Today we are going to look at some trig solving in kind of a unique way. We're going to solve things just normally by algebra methods, but we're also going to compare how that looks when we graph the solutions. You'll be looking for intersections then, and also how we graph things in polar form. So hang on, it's going to be quite a ride. All right, let's get started. First thing is just how do we solve a trig equation? And for you guys in your project, how do you set one up so that it comes out nicely? Well, first of all, how do I solve one? My initial goal would be to get one trig function equals a number, if possible. But that's not always possible. Sometimes you've got multiple trig equations, and we'll see an example of that too. But this one, I think I should be able to get sine of 3x alone. Once I have sine of 3x on one side and a number on the other, then I will do some sort of angle lookup, either typing it in my calculator or if it's one that comes out nicely, which this one will, then I'll just know it, right? Sine of 30 is 1/2 or something like that. And usually you're done, but sometimes there's some additional things that need to be considered. So initial goal here, I want to get sine squared of 3x alone. And so I don't like the 7, I don't like the 4, and so I'm going to subtract 7 from both sides and then divide both sides by 4. And so that gives me sine squared of 3x equals 1/4. Spoiler, you can see here, I'm going to need to take the square root to get sine alone. And so if you take the square root of both sides, see ya. Over here, this is just going to become sine. And on this side, square root of 1 over square root of 4, that's going to be 1 over 2. Now remember, if you do take the square root of both sides, that, still here, you will have to think about plus or minus. And so when you do that, that actually splits the equation up into two separate equations. And so over here, we're considering what happens if sine of 3x is negative 1/2, and what happens if sine of 3x is positive 1/2. In this case, if sine of 3x is negative 1/2, I'm looking up what angles give me sines of negative 1/2. And so those are going to be things in quadrant 3 and 4. And they're going to be 210 degrees, because that's the 30 degree in quadrant 3. And 330 is the 30-degree angle in quadrant 4. And usually we take those and add 360K to them because you can go around the circle and around the circle again and get more answers. When you look up sine of 3x equals 1/2, you get 30 and 150 plus 360K. And usually at this point you're done, but in this particular case, this wasn't x, it was 3x. And so if there's additional stuff that needs to be done to get x alone, well, we'll do that. In this case, we need to divide everything by 3. And so we divide the two base angles by 3. We also divide the period by 3. And so our complete solution would be 70, 110, 10, and 50, which I'd probably put in order, plus 120K. So that's the idea. I'd like to move to the side so you can see this whole thing. Maybe take a screenshot or pause it. And I'd like to see what does this look like if we graph it. So let's do that. I'll hop on Desmos to make the graph. And here is one that I've already done a little bit of ahead of time. So let me move these guys out of the way so we don't get distracted by them. So here is the left-hand side, y equals 4 sine squared of 3x plus 7. And here's the right-hand side, y equals 8. And so I'll turn those on a moment, and you'll see the left-hand side was a curve, and the right-hand side was a line. This is kind of the initial settings that Desmos has, and it by default thinks in radian mode. And so we answered the question thinking about it in degrees. And so if you hit the wrench and click to degrees, that would work. And then for Windows settings, you'll want to be able to see at least one full rotation. And so I'm going to suggest for the x-axis maybe going from 0 to 360 by maybe 90s, because that's one quadrant each. And I don't like the minor grid lines, I'll turn them off. The y-axis, depending on the picture, you may have to adjust. In this case, I think I can see the intersections just fine. And the x-coordinates of the intersections are what we're looking for. So 10 and 50, and here's one at 70, and here's one at 110. And those were the four that we had found. And then we had said that if you take any one of these four and add 120 to it, that would be another solution. So 10 plus 120 is over here at 130. 50 plus 120 is this one, 170, and so on. We continue on. Now, I actually noticed now, looking at the picture, that we could write our answers more succinctly than we could just by solving it algebraically. It looks like that this picture has a period of smaller than 120 degrees. It looks like it repeats every 60 degrees. And so if I simply wrote 10 plus 60 would give me 70, plus 60 would give me 130, and so forth. And 50 plus 60 would give me 110 and 170. And so I think a better answer for this would be 10 and 50 plus 60k. And it's not really a great way to see that without actually looking at a graph. All right, let's look at a slightly, well, slightly is an understatement, a more challenging problem. So here, this trig equation is 2 tangent of x plus sine of x plus 1, or equals 1 over secant of x. And the first thing I notice is it's a mixture of all sorts of things. Tangents, sines, secants, I don't like that. And so I'd like it to be just one trig function if we can. And so as an initial step, I think I'm going to do the trick of turning sines into cosine, or tangents into sines over cosines. Secant is 1 over cosine, and so forth. So if we rewrite it in terms of sines and cosines, we get this. Still a mess because there's stuff all over the place, but a little calmer because it's just sines and cosines at least. Now, I don't like the fractions, and so I would suggest multiplying everything by cosine of x, because this will clean up and this will get a little more complicated, but at least we won't have fractions in it anymore. If you do that, you've got this equation. But when you multiply both sides of the equation by cosine of x, you need to consider what happens if cosine of x equals 0. And so that's a little branch that we need to try to solve. And the solutions we get from this might be legitimate solutions. They might be extraneous solutions. They might be undefined. And so anyway, we need to think about them. And so right now, while I'm on this, why don't I think about that? Cosine of x equals 0. That means the width is 0. Widths of 0 are at 90 or at 270. And so let's look at, if we put a 90 into this or a 270 into this, does that make this true, false, or undefined? If we put a 90 in, tangent of 90, that's the slope of 90, that's undefined. And so already I can tell 90 and 270, these are not going to be solutions. But I had to at least think about them. So good to remember that. All right, back to our main branch here. So I've got stuff all over the place, and there's no great way to turn the sines into cosines or the cosines into sines. It works kind of well if you've got sine squared or cosine squared, because you can do the sine squared plus cosine squared equals 1 Pythagorean identity idea, but that's not going to help us here. What I see in this one is actually kind of unique to this problem. There's a 2 sine and a 2 sine here, and so I'm going to suggest, why don't we factor that out? And so if we factor the left-hand side, just pulling out that 2 sine, what's left behind is a 1 plus cosine. And that's actually kind of neat because on the right-hand side, I also have a 1 plus cosine. I know it's out of order, but you can swap those. And so that suggests a unique move. I want to divide that 1 plus cosine away from both sides. And so if I do that, it's messy right now, but if I divide both sides by 1 plus cosine of x, then the right-hand side becomes 2 sine of x, and the left-hand side simply becomes 1. And so that's, oops, I got ahead of myself. Where's that equation? There we go. No, that's not it either. There it is. The left-hand side becomes 2 sine of x, and the right-hand side is just 1, and that's a quick and easy one to solve. Divide both sides by 2 and do a few lookups, and we are done, kind of. Why don't we finish this branch a second, but we definitely have to also consider what happens if 1 plus cosine of x is 0. And so before I forget, let me put that equation on the side here so I don't forget it. No, I lost it. It's here somewhere. It's hard to see outside in the dark with sunglasses. Ah, there we go. Okay. So, let's see. 2 branches we have to solve them. This one, that one's not too hard. Sines are 1/2 at 30 and at 150. And so those should be legitimate solutions, plus 360k. And then, not sure what happens with this branch. We'd have to subtract a 1 from both sides. That gives us cosine of x is -1. So I'm looking at what angles give me -1 for a width. That would be 180, and that's it. So 180 plus 360k. And so we ought to think about, does that make the original equation true or false or undefined? If I put in a -180, it's not -180, I guess that's the same thing, -180 or +180. But if I put in 180 degrees, tangent of 180, the slope of 180 is 0. The height of 180 is 0. And so this would be 2 times 0 plus 2 times 0 is 0. On the right-hand side, secant of 180. Secant is 1 over cosine. Cosine of 180 is -1. And so the reciprocal of that would be -1. And 1 plus -1 is 0. And so 0 equals 0 is true. So that means 180 is a legitimate solution. And at this point, we're done solving things. I haven't found any other branches to explore. And so my final solutions should be 30, 150, and 180 plus 360k. Now, we ought to be able to confirm that by looking at a graph. And so why don't we do that a moment? So this one I had also typed up earlier. Let me bring those back up here. So y equals 2 times tangent of x plus 2 sine of x is this squirrely looking guy. And 1 plus secant of x is this one. And I'm looking for the intersections. So I'm going to make this just a little taller. I think I might be able to see in here. I think there's 2 intersections, but there's certainly one here. And that's at 30, like I expected. Looks like there's one here at 180 and one at 150, which is what we had said. If we zoom out a little bit, it's not super obvious, but I believe this pattern, yeah, this pattern is got a period of 360 degrees, which is what we said it should, and so that's good. And the intersections we found earlier, I think, were 90 and 270. If we look at the graph, 90 and 270 are places where both graphs are undefined. They have a, looks like they have a limit of positive infinity in this case and negative infinity over here. So anyhow, that is kind of cool. Now, so we've solved things by actual solving steps. We also solve by graphing using normal y equals screen, but we also learned this year how to solve things using polar form. And so here is a quick reminder of what polar form looks like. So this is our first equation, and instead of writing it in y equals something x form, I wrote it in r equals and theta form. And so to graph these, if we just turn them on, we've got this sort of picture, and it's kind of neat. I should suggest on a calculator, if you were going to do this, you'd have to switch modes to be in polar form. On Desmos, if you hit the wrench, instead of having the rectangular grid on, it makes more sense, I think, in this case to have the polar grid on. And I'm going to put our degrees back on there so we can see that again. And I'm not sure if we really need the axes numbers on there anymore. So here is a pretty cool looking picture. looks like a starfish in a circle of sorts. And again, the intersections are what we're going to be looking for. Unfortunately, Desmos does not allow us to simply click on them like it did before. Your calculator actually is a little better in this regard because you can trace and kind of walk along the graph and see that they intersect at around 10 degrees, and then again over here at about 50 degrees, and then again over here at 70 degrees, and so forth. And so that's kind of neat. So that's a polar form. The other equation, let me show that one a moment. That one is really squirrely looking. So if we turn those on, here are those two curves. And yeah, it's kind of strange looking. But if I look at the intersections, if I follow the green curve around, it looks like there's an intersection here. This is at 30 degrees. And then the green graph continues around, and there is another intersection, if you will, at 90 degrees. That's hard to see here, but no, I'm sorry, 90 is undefined. Where was the other one? At 150 degrees. So 150. Ugh. This one was a bit of a complex one to look at, finding the intersections. It's hard to see because they're at 0. Let me do this a moment. Let me add a 1 to both of these sides. So if I add a 1 to both sides, now those intersections wouldn't be at 0. They'll be over here at 150 degrees and over here at 180 degrees. It makes it a little bit easier to see. Anyway, that's a little bit of a review of polar form. We definitely have been using some calculators to do our polar form graphing, and that's okay. But I wanted you to at least see that and realize it's kind of more obvious in this example that the solutions we found by hand and the solutions we found by graphing and the solutions we find by polar graphing, they're all consistent. And that is one of the things that I love most about math is its design, its order, its consistency. It really makes me think and praise my God more because he created that to be orderly and defined and consistent. And I think it's amazing that he was able to realize all that was going to happen. And so that's one of the reasons I love math so much, because of all the different connections that can be made. So I hope you make some of those connections in your project. Just real quick, how do you make one of these equations to come out nicely? That's not obvious by any means. Most of the time, if you just randomly come up with a trig equation, it's going to have ugly answers. So how did I set this up to come out nicely? So I started off with sine squared of something, and I picked, I know that sines come out to be 1/2 occasionally, and so if I square a 1/2, I get 1/4. And I wanted that to turn into an integer, and so 1/4, if I multiply it by 4 or by 8 or by 12, that will turn into some sort of nice number. And so I chose 4, 1/4 times 4 is 1. And then I added some random stuff over here. I added 7, and so 1 plus 7 is, well, it's got to be an 8 in order to make it work. So you can do similar sort of thinking, but with a cosine. It doesn't have to be squared. You could do a tangent. If you have tangent, some of the nice tangent values are either zeros or 1s, right? You can get tangents of 1 or -1. Anyway, that's how I might recommend creating an equation of your own. If you want me to create one, I can. Just shoot me an email and I will send you something that will work nicely. Give me a couple of nice numbers that you want me to include, and try to make that happen for you. Anyway, sorry this video is a little long, but hope you have a wonderful day. We'll see you next time.